Okay, class, welcome back. As promised, I wanted to put on Sycamore in a YouTube video, a link to the YouTube video for the sample problem on limiting reactants. Sample problem says the black oxide of iron, Fe3O4, occurs in nature as the mineral magnetite. This substance can also be made in the laboratory by the reaction between red-hot iron and steam, according to the following equation. If I have 3 moles of solid iron and I react it with 4 moles of gaseous or steam water, it's going to yield our black oxide, the Fe3O4, as a solid, and it's also going to release hydrogen gas. It's going to produce 1 mole of the solid black oxide and 4 moles of the hydrogen gas. Okay, so this is what's going to happen under ideal conditions if I had plenty of, essentially if I had plenty of reactants, this wouldn't be a problem. But unfortunately, I start off with, according to the problem, and I'll keep it in red so you see it, I start off with 67 grams of the iron, okay? And I'm going to react that, okay, with 36 grams of water. So I want you to pretend these are beakers, okay? So in here I'm going to have, my liquid water. Okay, I've got 36 grams of water in here. Over here, I have a sample of red hot iron. Okay, now what's going to happen is I'm going to now mix them, okay, in a third reaction beaker. Okay, and our job is to figure out exactly what happens here. Now, as we discussed in class, okay, the limiting reactant is going to drive this. So essentially what's going to happen is when you mix these two together, you're going to produce this black oxide. Okay, now either there's going to be iron left in the reaction and the water is going to be used up, or there's going to be water left in this reaction and the iron's going to be up. Okay, so either we're going to be left with iron, used up the water, or we're going to be left with the water, using up the iron. So let me take all this back away, okay, as we begin to start this. Now you have a kind of a visual of mixing red hot iron with water. I had to use liquid water, though the equation clearly calls for steam, but it's easier to see it my way. Okay, when I mix those together, I'm going to produce this black oxide, and something's going to be left over. So, what we want to do here, okay, is talk about the limiting reactant. Okay, by definition, a limiting reactant is a reactant that limits the amount of the other reactant that can combine to form product, thereby limiting the amount of product. Okay, so limiting reactant, it limits how much of one reactant can combine with the other, and therefore the amount of product. So if we have a start of 36 grams, okay, 36 grams, I'll highlight in on this a little bit here, but if we start with 36 grams of the iron, 36 grams of the or 67 grams of the iron and 36 grams of the water, the first step in this process, as it always is we've got to convert mass to moles. That's what chapter 9 is all about. It's called stoichiometry. That's what we're going to be doing. So we're going to take each reactant, first in blue, okay? We'll take our 36 grams of water using the periodic table. You know that 1 mole of water equals 18 grams. So 36 divided by 18 gets us 2 moles. Secondly, we're going to do the same thing for 67 grams of iron. Again, looking at the periodic table, we know 1 mole of iron weighs 55.85 or has a mass of 55.85 grams. And 67 grams divided by 55.85 gives us 1.2 moles. So obviously, in terms of masses given, there's more water than there is iron. But that doesn't matter, okay? Because we have to use the molar ratio. We have to use the recipe to figure out in step 2 which one actually produces less product. That's exactly what we do in step 2. Okay, we compare mole ratios. So 2 moles of water comparing essentially this, the water, with the amount of iron oxide product, we see that for every 4, okay, I get 1. So it's a 4-to-1 ratio. So 2 moles divided by 4, I can produce, my water has the potential, the amount of water, 36 grams of water has the potential to produce a half a mole. If I do it with the iron, okay, again, we use the iron, okay, and we compare it with the iron oxide. We again compare, in this case, 3-to-1. It's a 3-to-1, so I end up dividing 1.2 by 3 to get 0.4. So clearly from this problem, the limiting reactant is the iron. It produces less of the product. The mass in grams, 36 grams of water, has the potential to produce half a mole of the product Fe3O4, and 67 grams of the iron has the potential to produce 0.4 moles of the product. Therefore, that guy, the iron, is your limiting reactant. Okay, so that's A. It says what mass in grams of black oxide is formed. That's pretty easy because we go back to the limiting reactant. Clearly, again, in part A, we found that the water has the potential to produce 0.5 moles, whereas the iron has the potential to produce 0.4 moles of the iron 3 oxide, or the black oxide. So obviously, this guy produces less product, and therefore the whole reaction will be driven by how much he does, how much iron produces of the product iron oxide, black oxide. Okay, so all we can produce in this is 0.4 moles of the product. Therefore, it says what is the mass in grams of black oxide that's formed? We simply since 67 grams of the iron produce 0.4 moles of product, we need to calculate the mass of grams of 0.4 moles of the product Fe3O4. So we do that using the periodic table. Fe3O4 is a molar mass of 231.55 grams. So we find out that 0.4 moles will produce 92.62 grams of iron 3 oxide, of the black oxide. So this is pretty straightforward. Where it gets a little bit confusing is in C. It says what mass in grams of excess reactant remains when the reaction is completed. This is probably the hardest problem of the chapter. Okay, this problem, what is the mass in grams of excess reactant? Okay, I told you in class, what's absolutely key for these things is that we keep in mind what exactly we are comparing. Okay, as I say here, it is of utmost importance that in completing these problems, we understand exactly what we are comparing. Okay, have to know that. That's why these are tricky, but if you get this, then you understand not only how to do it, but the reason why. And I said in science, especially biology, it's real important to put a reason why behind the how. Okay, so 2 answers to the problems. Pathway number 1 is compare reactant to reactant. Okay, so in the first section, A, we converted mass of our reactants, both the 36 grams of water and the 67 grams of iron, okay, into moles. Now, since we're just going to confuse, we're going to use one of those, okay, so we're going to start with 1.2 moles of iron, which we calculated in A. Okay, again, we're going to use the molar ratios now. We're comparing iron and water, and it's a 3-to-4 ratio. So we do it. For every 4 moles of water, I need 3 moles of iron. That's the molar ratio taken from the balanced chemical equation. 1.2 divided by 3 times 4 gives us. So again, 1.2 moles of iron divided by 3 times 4 gives us 1.6 moles of water. So what this is saying is we use 1.6 moles of water. Now, if you look back at A, 36 grams of water actually is contained in 2 moles of water, so we have the potential to use 2 moles, but all we use is 1.6 moles. So what we can do here is subtract 1.6 from 2 and get 0.4 moles, okay? And then multiply 0.4 times 36, the initial mass of the water, to get how much is left over, okay? What I did mistakenly, I'm solving for how much was actually consumed. So 1.6 moles of 2 available moles. Again, I'm here. According to my calculations, okay, if I start off with 1.2 moles of iron, which I calculated in A, and then I use the molar ratio to compare. Okay, for every 3 moles of iron, I get 4 moles of water. I need to react 4 moles of water with that. I'm going to come away with 1.6. That's moles of water, and if I multiply that by the molar mass, I figure out that I use 28.8 grams of water. But that's how much I consume. The problem is asking for what mass remains. So I'd simply, as a last step here, is I would simply go in here and say, okay, initially I started off with 36 grams. I consumed 28.8 grams. So I'm going to be left in my reaction vessel with 7.2 grams of water. That's how much is going to be left. Okay? That's the answer to C. That's the answer to C going pathway number 1. Pathway number 2 is just as viable, okay, where we can compare moles of reactant to moles of product, or go backwards, compare product to reactant. Okay, so we know that 1.2 moles of the iron will only produce 0.4 moles of the product. That's what we got in A again. It's the limiting reactant. So again, now we're comparing product to reactant. So we're looking at this guy, Fe3O4, and comparing it back to the limiting reactant, which we discovered was iron, and that is in a actually, we're not comparing it to iron because we already figured out iron's the limiting reactant. We're actually comparing it to water. We're looking for the excess. So if we start with 0.4 moles of Fe3O4, which is what the most we can produce because that's driven by the limiting reactant iron, we're trying to figure out how much is left in the reaction vessel. We multiply 0.4 times the molar ratio down here, 4:1. For every 4 moles of water, I produce 1 mole of the black oxide. And I end up getting, as we talked about before, okay, 1.6 moles of water. And again, when I multiply that by the molar mass of water, I get the same answer of 28.8. Now, that's the amount consumed. To figure out the amount left over, we'd simply subtract 28.8 from 36 to get 7.2 grams of water left over. So either way, comparing reactant to reactant and the molar ratios thereof, or comparing product to reactant and the molar ratios thereof, we are going to get the answer that we're looking for. Okay, that's really the problem as summed up here. Okay, good luck, and we'll talk about these. Well, God bless, there's no such thing as luck. We'll talk about these in class.